projects in that area, I thought looking at the walking machine takeouts, I'd add a takeout on my own. I think the first thing you learn about UAVs is that they're completely unforgiving. If you have an algorithm failure, you have a system failure of any description, then basically you lose $250,000 of sensors and aircraft and everything else along with it. And this was our first loss, incidentally. Something you can never predict. Unfortunately, it didn't have a nice explosion, but we lost all the sensors anyway. Is that, you know, in this case it turned out that the propeller delaminated. How can you design for something like that? All right, so you've really got to think through every single issue that you're doing in this. So the UAVs themselves are unforgiving, but even more complex is the fact that using many UAVs and trying to fly them basically all at the same time is exponentially hard, because not only do they all have to work, but you've got to also worry about the fact that all the perception and control problems are dealt with in real time, and that the communication is correct and all the fusion's happening and the coordination's all working and so on. Because these things are doing 200 kilometers an hour and you better damn well get it right. So this is a fairly tricky problem, and I'll just say a little bit about the algorithms just to show you how we actually addressed this whole system design issue. So DDF is basically a fairly simple idea. It basically says you've got a bunch of sensors, you don't want to have a central fusion thing, so what you do is you stick a fusion site at every sensor, and then what happens is you actually send fused estimates around the network, and every other node in the network also assimilates that information. And it turns out there are a lot of algorithms you can apply to systems like this, particularly those associated with the information filter, probabilistic techniques, the target tracking, cooperative navigation, and so on. Now, one of the cool things in the DDF is it turns out that they fuse everything locally, but what they actually talk about to each other turns out to be no more than mutual information. All right? That is the ratio of what I told you last time versus what I've got this time logged, and so on and so forth. So this mutual information really gives you a description or an abstraction of what it is this node is actually capable of applying or supplying to the network given any context or prior information. And it allows you at that point to actually abstract what each node is doing in terms of a software module. So you can see the software module up here is essentially presented as a likelihood function. It tells you what, in a raw form, that sensor is capable of doing. If you provide it with some prior information, which essentially tells you something about context, it will tell you what that sensor will do in a particular domain. All right? And the ratio of those two is the mutual information. And that mutual information tells you exactly what that node should do and how it should communicate information within that network. All right? So you've got a pretty simple now way of abstracting what one of those aircraft will do, and furthermore combining what lots of aircraft will do in a single architecture that you can actually prove what its performance will be before you build it. All right? Or before you run a particular scenario. And I'll point out here some work of some of my PhD students actually formalizing this in terms of standard software modules and so on. And here you can see one of the interfaces that allows us to switch on and off different sensors while the system's in flight. So we can actually test some of these survivability modularity components. So here is a good example. This is a deployment diagram, and in fact it turns out, you can't really read this, but here down here is one UAV, another UAV, there's a ground vehicle here, there's a human operator here, and so on. And within a few minutes or half an hour, you can reconfigure a system to run a completely different scenario. So you've actually got, in this instance at least, where you have information as what's going on in the network, a principled mechanism for actually building up a system and proving performance. And it's the kind of thing that we should be able to need in the sort of field applications that I'm interested in. So I thought I'd pick up on one project and show you the sort of outcomes. This is a program that was actually supported by the UK Ministry of Defence as well as BAE, and it was run by one of my good colleagues, Salah Zakaria. And it basically says the following: I've got a fleet of tactical UAVs. I give you a list of potential things that you ought to be able to go and look at, and what I want you to be able to do is to automatically figure out which aircraft should go and look at which target, in which pattern, etc., coordinate your activities, locate, identify, and effectively prosecute those targets. And this program was really a demonstration of this. I should perhaps also point out this is largely an implementation, in fact, of Ben Grotowski's thesis. So the metric in this case for control is just information gain, what comes out of those nets. So I'll just set up the algorithm. I won't say too much about that. The architecture, perhaps the most important thing to say in here is that everything is decided in real time. So you've got the basic fusion engine in here, the DDF algorithm that operates, but those estimates are then sent to the mission control system, which actually then decides on what mission parameters should happen on the basis of the sensor data while the aircraft are in the air flying around. Again, in field robotics, and surprisingly, I haven't heard anyone mention this so far in these talks, this need for having hardware-in-the-loop simulation, where you can actually take a vehicle, plug it into a computer, run the vehicle through the computer with simulated data, perhaps take data that you've logged from a previous experiment, and then run real flight data back through the aircraft on the ground, so you can actually check what's happening and who's doing what to whom, and so on and so forth. This is a really necessary part of doing any kind of large vehicle or difficult vehicle experimentation. We're fortunate, as I said, in Australia to have a lot of empty space. So University of Sydney, we own a big flight test facility. It's about the size of Rhode Island. And we have our own runways, hangars, living accommodation, and permanent authority to fly any aircraft we feel like flying off here. So big advantage over what you guys are allowed to do here. This project also involved the use of natural feature information as targets. And although I don't have much time to talk about it, I think I want to put an advert in here. Machine learning techniques, I was talking to Peter Cook earlier, have really made rapid advances in the last 5 years. And you can now really do real-time video processing on natural features like trees and dams and things like that for the sorts of times that we're interested in out of these aircraft using what are now fairly conventional machine learning techniques, in our case dimensionality reduction and things like that. So what does it look like? This gives you an idea of the flight. So this is a 2-vehicle flight test. So I'll emphasize again, it's not an automated takeoff or landing. We've got one pilot. He launches one aircraft. It goes into a holding pattern. He launches the second aircraft. It goes into a holding pattern. Then you take a deep intake of breath and hold, because if one of them fails, you've really got a problem. Then what happens is the system downloads all the potential targets to both aircraft, and then they start negotiating. So at that point, you've actually got no idea where the aircraft are going to fly. All right? And it depends very much on the sensor data that they see at the time and what they observe and what the initial conditions are as to what the performance will do. And just get to the bit where it actually shows what's going on. So here you can see the particular targets that they're interested in, the potential flight trajectories that they can have. These are the different footprints. So for this problem, we've actually parameterized the trajectories. So you can see here there are circles, straight lines, and various things like that. The other thing you've got to deal with is that these aircraft communicate using 802.11, so they go in and out of communication depending on whether they're banking and they're actually able to see each other. So you've got to be able to manage the fact that not all the time can they negotiate, just some of the time. And then they lock on, they make a decision on targets, and on the basis of that information, they then extract information, mutual information in this case. They share that information across vehicles. Once they've got enough information on target, they make another negotiation, and they decide who's going to what target. You can see there they get very close. This is a bearings-only problem, and the optimal flight trajectory for bearings-only sensors is to cross each other like that. Okay? But we cheat a little bit here. They're actually at different altitudes, so don't worry about them crashing in this case. So this gives you an idea of the sort of performance where we can, in terms of the system design, where we can take one vehicle, build that model, redeploy the software on a second vehicle, and actually guarantee the sort of performance levels that we're actually going to be able to get out of the system as a whole. That just shows you the typical data. We got various IR and camera information on the platform. So that's the kind of system component level that we're looking at. We've extended it in a number of ways. In particular, we've built more recently systems that involve not just aircraft but also ground vehicles, and perhaps more interestingly actually involve people inputting data into the information network. So they're actually modeled as part of the system and the way that they actually integrate. So not only are we then tracking, but we're also identifying and labeling different types of features. And perhaps in other work that we've been looking at, I should mention, these type of techniques, information gain, is applicable not just to these standard tracking problems, but also things like navigation. Search is an information gathering problem. Exploration is an information gathering problem. So all the systems engineering principles I've been talking about here apply equally as well to these kinds of problems. And in fact, we're now engaged in a number of projects that actually look at using distributed inference models in general as a method for modeling, abstract